This is Kosmographia, the Randall Carlson podcast. And welcome back, ladies and gentlemen, to the Kosmographia podcast with Randall Carlson. We are joined, as usual, by the usual suspects. Brad, how are you doing this week?
Better all the time, brother. Better all the time.
Better all the time. Mike, sir, how are you doing?
I'm fine. How are you?
Doing great. Kyle?
I'm doing pretty good, buddy.
All right,
How about you?
I'm doing great also. Randall, sir.
Sir, yes.
I've noticed you've got some interesting shapes on your shelf back there. Look at that.
Shapes on the shelf. Yes, those are shapes.
Surely you have a description of those.
Your background is very interesting today. That's what we're
right,
saying.
yeah.
Oh, well, I didn't have my green screen up, so I thought, you know what? I was planning to put it up, but why not have this for a change?
Yeah.
Yeah, those are just some of the 5 regular polyhedra, also known as platonic solids. Although those aren't solids; those are edge models. We make those, and we're going to be, of course, making model kits available when the new HowTube site is launched in a couple of weeks, the 18th, after the 18th. So, yeah, they're.
Oh, yeah.
It's a
Dodeca.
I originally developed these for use in my classes, and you know the kids loved them. We would build these models. I would provide the pieces already pre-cut, and then the kids would put them together to learn about what is a regular polyhedra. Kyle, what is a regular polyhedra?
I don't know.
Really, really disappointed in you at this moment, Kyle. A regular polyhedra is simply a solid shape where each of the faces is identical. That's all there is to it.
Okay. Now I know.
Right. So then you also have the semi-regular, but that's where you can combine to get 3-dimensional forms where the faces are not necessarily all the same. But the regular polyhedra, there's only 5 of them. You know, this is my favorite. This is the dodecahedron, and at some point we're going to do a show. We'll do an episode where we talk about the remarkable properties of these particular figures. Particularly
That one has 12 sides. Is that
it
right?
has 12 faces. Yes,
12 faces. Right.
12 faces.
All right. So, yeah, each 12 pentagons. So the total of the angles within the pentagons is 540 degrees, correct? Times 12.
Very good. Yes.
Gives you, I'm guessing here, I don't remember exactly, is that 6480? So that's a season of the great year that is replayed in that shape.
Well, in this shape, in this form here, we have 12 pentagonal faces. And like you said, each angle, right? Each angle of the pentagonal faces is 108 degrees.
108, yep.
Okay, this was one of the fundamental numbers in the archaic systems of proportioning and mensuration and architecture and so on. 108. So then 5 times 108, that's where you get your 540. And then that times 12 gives you the total number of degrees that comprises the dodecahedron. Dodeca means 12 and hedron means faces or sides. So 6,480. And it turns out that number is a rather interesting number in terms of archaic traditions because it is the number of years in the idealized traditional season of the great year cycle.
How did that happen?
Well, it's just, it may have meaning or it may not have meaning. It's interesting, though, that when we look at each of the solids in turn and derive this total degree measurement associated with each one, we do get an interesting series of numbers. So I don't have a cube back there, but in the cube, there's a total of 2,160 degrees, which we know then would be a month.
1 month.
3 months of the great year is a season. And so 3 times 2,160 is 6,480. And then twice 6,480 gives us the 12,960. That's only a century in excess of the whole Younger Dryas impact event that we've been talking about for weeks now. Which is,
you tried to jump by it, but I'm not going to let it slide, Kyle. You're going to like this because 2160, right? Everybody, diameter of the moon.
That's right. It's the diameter of the moon.
In feet?
Miles.
In miles.
Miles.
in feet. In miles, yes. But of course, that's only when you measure it in miles. That's a significant number. And actually, if you measure it in kilometers, it's going to be closer to 1,000, or the radius, I think, 1,738. Because if you've got 2,160 miles in a diameter, that means 1,080 miles comprises the
radius.
The radius, which is very close to 1,738 kilometers. So, but of course, the moon is not a perfect sphere. So this is an idealized model. This is not the actual moon. I just want to be clear on that. Just like we could say that 7,920 is the diameter of the Earth, but the diameter of the Earth is not consistent. It varies depending on your latitude, right?
Right.
In fact, let me ask you guys, how much, let's suppose you were at the center of the Earth, Russ, and you had to dig your way to the surface. So how many miles less would you have to dig your way to the surface if you dug your way out at the North or South Pole compared to if you dug the hole out to the equator?
I don't remember the exact number.
In other words,
like
what is the difference
13,
between equatorial radius and polar radius?
Yeah, it would be 12 or 13 miles less.
Yeah, 13,
I was going to say
miles.
I was going to say 14. Yeah, I'm trying to remember which episode that was. So yeah, we're in the range. 13
in the range.
Okay.
Yeah, but 13 is going to be much closer
because it's 26-mile difference. Go ahead, Rand.
Well, yeah, 26-mile difference in diameters.
Okay, yeah,
and so that it's the spinning. It's because the Earth is not a perfectly rigid mass. It's a plastic mass. So as it spins, mass of the Earth migrates towards the equator of the spin.
But if you were in the center
of the rotation,
if you were in the center of the flat Earth, then
you don't have to dig very far to get out.
You don't have to dig at all. You just...
Well, that's true. Yes, that's true.
It's just a manhole cover.
Now, okay, so is this like a revelation here, Kyle, that I have been unaware of? That you're not? Are you an advocate of the flat Earth model?
We discuss it quite often.
Yeah, I like to throw it in, occasionally when we're discussing.
Well, here's the irony is that actually a flat Earth model is very useful in some cases, particularly when you're making astronomical observations and you're projecting the celestial sphere down onto a flat surface, because even though the Earth is spherical, quasi-spherical, because it's actually an oblate spheroid, and somebody was challenging that I at one point a while back, and I saw one of the comments. And you say, well, no, you can, if it was shrunk down to the size of a billiard ball or something.
Billiard ball, yes.
Was that it? Yeah. But the fact is, look, like we were just talking about, there is a 13-mile difference. So, we want to, nitpick here. Look, that 13 miles difference means it is not a perfect sphere, okay? So even though relative to the entire size of the Earth as a whole, it's very, very small. Look, we're dealing with very precise measurements here. So 13 miles is pretty significant. But without that 13 miles, we're screwed, right? That 13 miles acts like a flywheel that helps keep the Earth.
Yeah, I was going to say, yes, there's a...
Yeah. So whoever designed the system, made sure that the plasticity of the Earth was just ideal so that it wasn't too extreme, but there was enough still to keep the Earth relatively stable. So, at least whoever they were, and I tend to think it was a team effort myself.
I'm
Yeah.
gonna have to think about that.
See, I think, well, look at it this way. The system is pretty damn impressive, but it ain't perfect. So that has led me to conclude that it was largely executed by a group of subcontractors. and they probably were they probably needed a little bit more, management, but under the circumstances, I think they did pretty good. But overall, there's some flaws. And maybe at some point, that's what we need to be addressing. We, the human species, need to address some of those flaws.
The flaws, yeah.
It looks good on paper. With a little tweaking, I think that the system could work a whole lot more effectively. Right.
Great work.
So, yes. Well, see, the thing we have to ask is there a connection between the energy fields of the Earth, which exist? The geomagnetic field exists, right? Electromagnetic fields exist. Those things are dynamic. The question is do they, or is it outrageous to assume that these changing ambient fields in which we find our delicate nervous systems immersed, the changes in these dynamic fields would not affect us on various levels, physically, emotionally, mentally, psychologically? Is that not possible? And in fact, we could further ask the question is, have people throughout history sometimes understood that maybe that is possible, and that there are certain things that could be done to actually gently massage those fields, those ambient fields, to get a more salubrious result, if you want to put it that way? Well, I think that perhaps once we begin to study into some of the specifics of these things that these ancients were up to that otherwise don't seem to make sense. Like, why would they build a 82 foot tall pyramid just to put a pharaoh in? No, there was another reason for why they did that. Not only is it prominently out there, like where you can't miss the damn thing, if we reconstruct in our minds and we resheathe it, we put the sheathing of the highly polished white limestone casing, right? Well, what on earth? I mean, we're looking at something there that is just phenomenal effort, a phenomenal work of architecture. And to think that it was built by basically slaves or basically subsistence farmers. I mean, who lived in the Egyptian Old Kingdom, if we even accept that that's when it was built? In the Nile Valley, it was mostly farmers, right? And yet here's this monument, this incredible, and to think then that, or to think of it in such a way that there's no disparity really between the cultural model of a civilization that's largely composed of subsistence farmers living in the Nile Valley, and to execute something like the pyramids. I'm sorry, there's just a major disconnect there. And I can't even imagine that. I think maybe in some cases it's so glaring and so out of context. That's what it is. It's out of context. But in that case, in that way, it's not alone. There's so many things from ancient times that are out of context. And it's those out of context things, I think, that collectively we look at it and we go, wait a minute, there's more to this story. There's more to this story than, and as our ability to recreate the events of the past and perceive into the past and put these things, just like we've been talking about for the last 5 or 6 episodes, where we're looking microscopically now using, energy dispersive spectroscopy. Nobody was using that 40 or 50 years ago. So you couldn't really identify these things to the level that we can now, or transmission electron micrography. All of these things, these technologies that are allowing us to go in and see this stuff that's there hidden in the landscape, right? And then to have that stuff begin to reveal its story to us. This is just, to me, amazing. It's an amazing thing. But as we keep going forward, assuming that we can, and as long as we can keep learning and keep growing, and science can keep moving forward, we're going to get better and better able to be able to decipher the events of the past. And I think as we do, we're going to really go, yeah. We really do need to reevaluate what might have been going on in terms of human history back in the era before we were keeping a written record. I think that's almost at this point a foregone conclusion. So go, yeah.
We seem to always want to use all of these new scientific methods to confirm the previous theories before we had those methods.
Mm-hmm.
Say, yes, we were right before we had this tool to look deeper. You know, we talk about this all the time. There's this resistance to the possibility that the prevailing theories may be wrong, when even though we keep getting better and better tools to look deeper and in more detail. You know what I'm saying?
Yeah. Well, and this is why, you know, you really, you know, what Carl Sagan used to say, right? It was Carl that used to say this, right? Extraordinary claims require extraordinary proofs. And I've always believed that, you know, and I believe that some of the claims being made about the younger Dryas boundary events are quite extraordinary. And in fact, this paper that we're going to be looking at tonight, in fact, is even entitled, you know, Extraordinary Biomass Burning. There we go. Extraordinary biomass burning. Not just like normal, regular biomass burning, but extraordinary biomass burning. So you're going to make an extraordinary claim, you got to provide some extraordinary evidence. This is exactly what the Comet research team has been doing now for 13 years, is being able to meet every objection, to meet every criticism, almost, not quite, because there's still so much that needs to be learned about this event. So many insights that still await us, because we really haven't figured it out yet. However, when we dive into the paper here, you know, I think we have a pretty good scenario that I think is getting really close, and we'll get into that as we go along here. What it is that might have happened, and I think we can begin to reconstruct with a high degree, a high degree of confidence that we're honing in on what it was that happened. But yeah, this is why it's so important to get into the details of the thing, and to belabor some of this stuff. You have to belabor some of it, or otherwise, you know, part of the problem with modern education is its superficiality, and people being afraid to dive into something deep and really, really invest the time to put the pieces together. But there are people out there who thrive on that, who know that that's necessary. And I think those are the kind of people who are going to be tuning in and listening to our attempts to put this information together. And of course, we don't have the final answers, and sometimes we make mistakes, and occasionally we'll mispronounce a word, which does happen. And so if we make a mistake, somebody did actually, I think, made an issue and said, because of a micrometer, said, well, it's not micrometer, it's micron. But actually, like, this is a good example of somebody trying to correct us. Didn't one of you guys tell me that there was a
it's micrometer and microns.
Well, a micrometer is the instrument, but a micrometer is the same as a micron. If you look it up in the dictionary, you'll see that they're synonyms, right? Okay. And I may have misspoke and said micrometer when I was meaning to say micrometer when I meant to say micrometer.
Like you just did there.
Yeah, exactly. And you see, part of the problem is when you're trying to expound upon this stuff, part of your brain is always like, where are you going with it? Because you don't want to just ramble. So you're like already thinking ahead, what's the next sentence or the next paragraph? Where am I going with this thing? So what happens is it disengages a little bit. And so, yeah, you make a mistake like that. You say micrometer instead of a micrometer. But I think most people knew what I was talking about.
I do too.
But I do like micron. Micron is nice and simple and clean. So from now on, I am going to use the word micron when I'm talking about a millionth of a meter, okay?
Man, that's what I've been doing wrong this whole time. I haven't been thinking ahead, and that's why I say really dumb stuff sometimes. So I'll try to do that more.
See, that's why. Because Kyle, the strategy there is when you say really dumb stuff, it makes me look smarter.
I'm trying to make the host look good.
That's right. Yeah.
So
our job is to make Randall look really, really smart, which is not hard, but we're pretty good at it. We can be dumb pretty easily.
I have my dumb
was still
moments.
processing. Well, I'm an associate or I'm an assistant. I'm an ass either way.
That's right. Well, Brad knows how to.
I know what you were trying to get to there.
Yeah. Either way, yeah. Brad's No, if he was, I probably wouldn't be able to, put up with him all these years. No, don't have too many complaints about Brad. And what complaints I have are, pretty minor.
They're only about evil Brad.
Though.
Well, evil Brad. Well, you guys have never seen evil Brad. And it's not you don't want to see evil Brad, okay? Oh, wait a minute. We all
saw evil Brad.
Evil Brad. We
yes.
did. Oh my God, yes. The memory of that. We saw that in Colorado, didn't we?
That's right. It was terrifying.
It was.
I was scarred for life.
It was traumatic. Yes, I suffered from PTSD for the rest of that trip.
I'm amused that you think that was the evil. I was only like a third of the way there.
Oh my God. Oh my God.
Wow, that's even more scary.
That is more scary.
Let's talk about the younger Dryas. I can't handle this conversation. It's terrifying.
Sorry for that diversion.
Extraordinary biomass burning is much less scary. Let's talk about that.
Right. Right. Absolutely. Yeah. A large part of the Earth's surface being consumed in hellacious fires. Yes, that's
is less scary than evil Brad. Yeah, that's what we're saying.
So anyways, okay. So then in 2018, there was a couple of papers, both published in the same issue of the Journal of Geology. Lead author was Wendy Wolbach, Wolbach probably, but a bunch of other authors. Let's see, I don't even count them here. So it came out in two parts. Part one was looking at the evidence that was preserved in ice cores and glaciers for biomass, extraordinary biomass burning. The second paper was looking at marine, from the ocean, marine records, lake records, and terrestrial sediment. So the second paper, marine, lake, and terrestrial sediments. First paper, glaciers and ice cores, right? So the purpose of these two back-to-back papers done by this team, and I will, let's see, where's the team? Here we go. So you'll see here, I'll just do a very quick share screen of this. You can see this is the full team right here. I counted these at one point, but you'll notice, let's see, our good friend George is number 7 here in the team, and hopefully over the next few months, we're going to get a few more of these folks on to talk about their specific work and specific contribution to this extraordinary phenomena here. So that is the group, but the lead author is Wendy Wolbach. And so, anyways, let's dive into.
She goes back. She's one of the. Excuse me, just to reconnect. Yeah. She's one of the few, if not the only, that had done work on the KT boundary. Also, the biomass burning that happened with the studies of the asteroid that hit in the Yucatan from the dinosaur killer.
Yes, exactly. And I think I probably read, because I started following the Cretaceous Tertiary controversies really right after they got proposed in 1980 by the Alvarez team and two other teams that same year. But I think her initial work came out maybe mid to late 80s, where she began really looking at the evidence for extensive biomass conflagration associated with the KT boundary. And so that was why I first encountered her work and read several, and she had a number of subsequent articles and papers that she authored. So I already knew
that was 84. So it's
pretty early
3.5
on.
Decades she's been.
Yeah, so she's been on this for a long time and knows her stuff. Anyway, so seeing her name then attached to the younger Dryas was gratifying to me, because I always, I've cited her work literally decades ago in talking about the events surrounding the Cretaceous Tertiary and the extinction of the dinosaurs. So they start out the paper by saying, referring back to Firestone and the original paper of 2007, the seminal paper that kind of started this whole controversy, lead author Richard Firestone. So they point out that he initially posited that exotic materials found in the Younger Dryas boundary layer provide evidence of a major cosmic impact event caused by Earth's collision, now get this, with a cometary swarm 12,800 calendar years ago at the onset of the Younger Dryas climate episode. Studies of more than 40 sedimentary sequences distributed across North and South America, Western Europe, and Western Asia all document peaks in exotic YDB materials, including, let's go through this list now of these things that we're learning about here, because these are all signatures, right? Including high temperature, iron-rich spherules, silica-rich glassy spherules, melt glass, nanodiamonds, iridium, platinum, and osmium. Well, so the paper goes on to say that independent groups have confirmed much of the YDB impact evidence, but others have not or have offered alternate explanations. Now, we've talked about some of the alternate explanations, some of the papers that did not confirm the finding of impact-related evidence. We could have gone into that, spend more time on that, but I kind of wanted to convey the gist of it so that people kind of understood that what the first objections were, the criticisms to the impact hypothesis, and then how the proponents of the impact hypothesis have responded to those criticisms, because that's an important part of how the scientific process works. Now, at some point, it would be good to have a review of that and really tabulate looking at the back and forth between the two groups. I think we're at the point now, though, where we've seen some recent defections from the skeptical camp, including Michael Shermer and Mark DeFant. And see,
yep.
You know, to me, those guys, I consider their objections extremely valuable and important, right? Because what has to happen is you have to challenge, you know, and a lot of times the criticisms, if they don't hold up, you know, it's through their very, let's say, weakness that it's sort of almost, you know, by default then confirms the positive interpretation of the evidence. So in this case, if you look, for example, if we look at explanations for the great mega floods, we find that early on there were a lot of explanations that tried to explain the geomorphic evidence of these giant mega floods in terms of more normal gradualistic scenarios. But the more they attempted to do that, the more it became glaringly obvious that these explanations just didn't work. In terms of you might be able to invoke a gradualistic or uniformitarian or more normal process for like one aspect of the evidence. But then when you start looking at the totality, that's where they just begin to fall apart and become glaring in their deficiency. They become just, you know, very, very, very prominently wrong. You can see that, no, it just doesn't fit anymore. Well, I think we're seeing a process, kind of a winnowing process, like with the Younger Dryas theory. We find that the same thing happened with the KT boundary. And the primary controversy now about the mass extinction, which is pretty much, as far as the KT boundary, is not so much whether or not a mass extinction happened, but what was the confluence of forces that caused it. I would say that at this point, the impact hypothesis is the dominant one, but clearly the extrusion of the Deccan Traps volcanism in India played a very significant role in changing the global climate at a critical time. So I've pretty much concluded that in what we're seeing, and we're going to be examining this in their own time, the so-called 5 great mass extinctions in Earth history, when a vast majority of all existing species or even genera disappeared from the record, right? And what you see is when you look at all of the great 5, and this is the Younger Dryas extinction is not included in that, right? Because we're talking about taxa that runs through the entire gamut of the food chain, even down to, microscopic zoological and planktonic and benthic forams and so on in the ocean column that disappear, right? We don't see anything like that at the Younger Dryas. What we see at the Younger Dryas is the megafauna. We see the bigger animals disappearing, and we've talked about there's reasons for that. But the point is you've got several things that are happening at the same time. Each of the big 5 has the signature of a cosmic event. Now, at the KT, it's much more prominent. The other 4, though, also have signatures, but not enough to declare categorically or definitively that, oh, yes, it was caused by an impact, right? But all 5 also have the signature of huge volcanic events happening, co-occurrence with the loss of species. When we go through that evidence, you'll see that what it appears is that you've got an exogenic component. In other words, there's a volcanic eruption, huge amounts of volcanic material extruding to the Earth's surface, which emits tremendous amounts of pollutants into the Earth's atmosphere. The sulfur-based compounds and things that could create a global haze that can bring about substantial cooling because it's reflecting sunlight, right? So you've got an endogenic coming from within the Earth, but then you've got the exogenic coming from without the Earth. My suspicion at this point is that the fundamental driver of this, the dominant one, the primary one, is the exogenic. So that you might have an exogenic event that triggers an instability within the equilibrium of the Earth, and the response of that is going to be volcanic activity, or maybe perhaps seismic activity. But the volcanic activity leaves a very definite signature in the geological record that can be studied. And so, just like at the Permian Triassic, which was the greatest mass extinction in Earth history, there is a platinum group metal signature there. There's an iridium signature, but there's also the extrusion of the Siberian traps. So you had this tremendous, huge outflowing of molten mantle material. Interestingly, extruding, the epicenter of extrusion is pretty much right dead on, almost like a target of the Tunguska explosion. Coincidence? Yep. I don't know. But we'll be looking at that because literally, it's as if the Tunguska object came in, zeroed in on the target, and exploded. And dead center on that target is the center of the extrusion zone of the Siberian traps that was associated with the greatest mass death, planetary mass death in the history of the Earth. Just an interesting little coincidence, and we'll look at that. But so what I'm getting at is it appears to me that the great mass extinction events are likely involving both endogenic and exogenic. And the exogenic, I would say, if I had to speculate, I would say that the exogenic is probably the thing that is tends to be the causal effect, and the endogenic is more of a response, an effect of that causal event. Because, if you take something the size of Mount Everest and you accelerate it to 10 times the speed of a powerful rifle bullet and slam that into the Earth, it's going to have consequences. And I think those consequences are going to be transmitted throughout the entire lithosphere. And I think that there has to be, with an injection of that much energy into the system, I think there has to be some type of a response, a rheological response from the mass of the Earth. How could there not be? And then that may in turn lead to increased volcanism. And then that increased volcanism has a lot of other consequences now that could perhaps interact with the direct consequences of great impacts. Anyhow, I digress. So we've got iron-rich spherules, silica-rich glassy spherules, melt glass, nanodiamonds, platinum, osmium, which are both part of the platinum group metals, iridium, right? Now, these are the fingerprints. These are the things that we can't see with our naked eye, but they've been there hiding all along, waiting until we develop microscopes powerful enough to find them and to technologies to find them. And then, of course, they laid there for decades. Even though we had the technology, it never occurred to anybody, well, let's go look. And if it did occur to them, where would they know where to look? Well, until Vance Haynes came along and did his work, which was to say, look, there's this ubiquitous black mat layer, and it's really unusual, and we need to figure out why it seems to be associated with megafauna. Boom, they're below the black mat, not above it, with a few exceptional cases. But overall, megafauna is below, not above. And then we've got this North American culture that showed up from who knows where, mysteriously, left artifacts all over the damn continent, and they disappear right below this boundary. And then we see something else. We see that boundary is associated with this sudden massive climate spasm that probably cooled the northern hemisphere by 7 to 10 degrees centigrade in a very short while, less than a few years, right? So now we've got these things associated. So what that did was finally inspired Firestone to go take a closer look at the black mat. And when he did, that's when these things begin to turn up. So, but now here's the question. If these nanodiamonds are showing, which we haven't gotten into really addressing in depth yet, the nanodiamonds, but if this, say the microspherules and the iridium and the platinum and stuff is showing up at this boundary, the question is this unique? Is this unique at this point? In other words, if there's an enhancement or a spike of these things, then is that spike unique to the base of this black mat? I mean, do we look, because if it's diffused throughout the stratigraphic column, it probably doesn't mean anything too special, would it? So, but if there's a clear spike and then below it or above it, for example, if you find a layer of nanodiamonds but there's basically none below it and none above it, it tells you, well, that's probably something special, right? But now what happens if you find those nanodiamonds associated with a spike in polycyclic aromatic hydrocarbons or a spike of soot? That's interesting, isn't it? It brings this whole other dimension to it, see? So the team goes on here to say, an anomalously high peak in platinum concentrations recorded in sediments and ice. Now, we went back to Patave. God, I'm going to find out how to pronounce his name properly at some point, and I apologize to you if I'm mispronouncing your name. But we did talk about his paper, because he was the one who discovered the spike of platinum in the Greenland ice cores in the first place, right? Because what he decided, again, motivated by the work of others, he says, well, guess what? I'll go back and look at the ice cores at that date, the date that coincides with the black mat layer, and see if there's anything that shows up in the ice cores, right? So that's what he did. And when he looked there, what do you think he found? Oh, he found a platinum spike, part of the platinum group metals, which are consistent with an extraterrestrial delivery of some kind. So they go on in this paper, and an anomalously high peak in platinum concentrations recorded in sediments and ice has been reported at or close to the younger Dryas onset across North America, Western Europe, and Western Asia at 26 sites, including an additional 8 sites in this contribution. Patev initially discovered this platinum peak spanning approximately 21 years that began precisely at the onset of the Younger Dryas climate episode in the Greenland Ice Sheet Project ice core. So that was the first time anybody had made that connection, right? Now, this spike, this climate change spike, this extraordinarily fast and very severe climate change spike had been identified by the early 90s, right? But we're here now looking at 2018. Let's see, when was Patiev's paper, which is a few years younger than this. But the point is that you come from 93 to 2000, it might have been 20 years later, right? That suddenly somebody is looking at this spike where the climate just spazzed out and then discover, wow, there's a very substantial deposition of platinum there. So what the hell does that mean? And it's being found, look at how widespread. You got North America, you got Europe, you've got Western Asia, and let's see. So yes, what are we to make of that? So, and then the platinum spanned for 21 years. In other words, what these ice cores showed was that for 2 decades, basically, the Earth was being dusted with platinum. And the onset of that global platinum dusting coincided with this rapid drop in global temperature. So what does that mean? So let's go and take a look here at some cool graphs.
We could take a quick break and come back and look at some of these really cool graphs.
I have a good idea. Why don't we take a quick break, then we'll come back and look at some cool graphs.
Sounds like a fantastic idea.
Okay.
We'll be right back, folks. And we're back, ladies and gentlemen. About to get into the facts and figures. Randall's going to show us this is the 2018 Wolbach paper, correct?
Mm-hmm. Mm-hmm.
All right. I can tell by the eyebrow that.
Yes. Extraordinary biomass-burning episode and impact winter triggered by the younger Dryas cosmic impact approximately 12,800 years ago. That's the title of the paper. And part 1 is it's its own standalone paper, is ice cores and glacier. So that is what we're looking at first. So I'm going to pull up a graph and we will have a look here and try to do a little bit of deciphering. Okay, so there's a bunch of stuff going on here. Notice the dates. Now, this gray bar, let's look at the calendar years at the bottom. You'll see that over on the left is 13,000 years ago, and then on the right is 12,700. So this graph, the x-axis spans a 300-year time span, right? And you see this width of this gray bar. This is the 21 years of platinum deposition. And as we come forward, you'll see that the beginning of this bar comes up here, and then there's this spike in this dark, the dark graph here. And you'll notice there's a bunch of these sort of gray colored graphs down here below. So as it says over here, this is the platinum record compared to cumulative concentrations of sea salt and continental dust. So this is the platinum concentrations over here. And you'll see as you're coming along from 13,000 years ago, you come in right here, it takes a dive, and then it starts climbing. And then right here, there's a spike that exactly coincides with the onset of the younger Dryas. It continues to climb to this dotted line, and that dotted line actually represents the date of the the combustion proxies in the ice core. So the combustion proxies coincide with the largest spike in platinum. And then down here, these gray, various shades of gray graphs, you'll notice up here they represent chlorine, magnesium, calcium, potassium, sodium, platinum, right? Well, this is platinum. But those things are coming, the chlorine, the calcium, the sodium, magnesium. What's the source of those? Well, both from the ocean and also from the continents. So what's interesting about that is that you'll notice right here, let's see, this one is the, looks like the potassium and the sodium. Well, like three of them have a huge spike right here at the beginning, right again, exactly coinciding with the onset of the Younger Dryas. And then you'll see that for the next couple of hundred years, they climb way up. And notice here this huge spike over here, which is dated at 12,711 years before present, right? So this is right here early within the Younger Dryas. You see that that the chlorine, the magnesium, the calcium, the potassium, the sodium is all climbing, right? So where is that stuff coming from? Well, a lot of it is coming from the continent. It's the signature of dust that's blowing off of the continents and settling into the ice sheet. So basically what you're looking at there would be, yes, climate related. So the asterisk coincides precisely with a peak at the onset of climate related dustiness right here, rising to an anomalous dust peak that is higher than 99.7% of values in the previous 100,000 years. Okay, so here's what you've got. Here's the significance of that. It's that right there, coinciding with the onset of the Younger Dryas, you suddenly have this huge flux in continental dustiness. What do you think that implies, Kyle? Now, all of a sudden, you've got dust being blown off.
Like, I mean, crazy storms.
Lack of biomass to hold it down.
Like, yeah, so
exactly.
After you have a huge fire, then there's just a bunch of ash and dust laying around, and it picks up in the wind.
Right. What you're seeing right here, these graphs of these various elements, the chlorine, the magnesium, etc. That right there, you could think of as the signature of the wasteland. The wasteland that has been now deprived of biomass, of vegetation. So you're basically looking at the signature of a very large barren landscape that is now yielding up an immense amounts of dust. And yes, increased storminess and increased wind may be a factor as well. And it would make sense in a way that you would have increased wind and storminess. But that is what this interesting graph is telling you right here. See, is it right in the aftermath of the Younger Dryas? You've got a continental landmass that apparently is barren of vegetation and biomass. So that's basically what the point of this graph right here. If we look at these graphs, here's one that goes back, way back. So we started 5,000 years now. 5,000 years ago, back to, well, let's see, that's 105,000 years ago. So this is what the caption to that particular graph says. This is from A is going to be NH4 is ammonium, right? Now ammonium is a proxy for biomass burning. Biomass combustion produces a suite of these various substances. One of them is ammonium. So NH4 was produced, notice right here, notice that there was this, look at the amount of ammonium that's deposited in the ice going back, let's see, it says the most dramatic rise culminating in the most robust peak coincides with the platinum peak, which is the dashed line. Check it out. Check it out. What we're showing here, this up and down here, this is ammonium. Ammonium is produced by the combustion of biomass. Now, look what the ammonium does. It spikes right here. And notice that that spike is precisely the same as the spike of the platinum in the Greenland ice core. So now we got these two things. We've got the ammonium, which is a proxy for biomass burning, exactly coinciding with platinum, a platinum spike. Very interesting. So we see that the platinum is deposited, and then right in the aftermath of that, we see huge amounts of ammonium. Now, there are other proxies as well that are produced, a whole host of substances that are produced by wildfires, by intense biomass burning fires, right? Ammonium is just one of them. But if we look over here at the second graph, notice that we see the ammonium, the NH4, is this dark line at the bottom, right? And here's what it says about it. This is the oxygen 18, which is the gray up here. And oxygen 18 isotope, remember, is a proxy for temperature change. Now, in this one, as the heavier oxygen goes up, that's correlating with the temperature getting colder. So if we go back, notice here, you're back just at 13,000 something at the beginning of this graph over on the left. And then you come through to follow this gray box-like graph here. This is representing shifts in the oxygen isotope ratios, oxygen 18 to oxygen 16. So as that ratio shifts, that is a shifting in response to the climate warming and cooling, warming and cooling, warming and cooling. So you'll see that right here, you have this huge spike of shift in the oxygen 18 isotope, and it's an indicator of cooling. And notice it just comes right into the early part of the younger Dryas. So now we're correlating something else. We see that there's a major drop in northern hemisphere temperature that's associated with the beginning, or very, very early in the younger Dryas. We also see that there's a spike right here of ammonium. And notice that the spike of ammonium, you follow that up as it's pointing out, this dark arrow comes down pointing to the spike of ammonium. It comes up, it coincides exactly with that sudden 6 to 8 degree cooling of the northern hemisphere temperature. And then we come through the younger Dryas, and the climate just keeps getting colder and colder. And then something happens here, which really has not really gotten a lot of attention. But notice that the isotopic shift is taking place, and that isotopic shift represents a warming, right? And notice that it is associated with the biggest of the ammonium spikes right there. So now that might make sense, because if you've got a landscape that's been largely, the biomass has been destroyed. You've got and on top of that, you've got this temperature, this drastic temperature drop. Now, think about trees and vegetation that survived a fire. Now you've got a shift in temperature that's very significant. That's like shifting from the southern United States to the northern United States, almost. That's severe. What's going to happen to any remnant biomass? A lot of it's going to die as a result of that climate change. So throughout the course of the early younger Dryas, what seems likely is that there was a huge accumulation of dead and dying biomass that provided the fuel for subsequent catastrophic firestorms, even without further impacts. Although we shouldn't necessarily try to say that the impact episodes, and we're going to come back to talk about that the impact episodes episode was maybe not confined to a single event, right? So B is the oxygen 18 isotopic record from 120,000 to 100 to 5,000 years. Oops, I'm sorry. I'm reading wrong. That was A. Yeah, this is actually C. So C is Platinum anomaly from 12,836 to 12,815 calibrated years before present, with ammonium measurements, which is the solid black curve, between 13,050 and 12,600. Okay, so 13,050 years ago over here on the vertical axis, down to 12,600 years ago on the right vertical axis. So the stair-step plot with the lower values representing colder temperatures, dotted lines are basically low S curves, which are just basically to help visualize the trend, right? The trend. So you'll see that the trend of the amount of ammonium being deposited into the ice sheets is increasing in the first 2 centuries of the younger Dryas. So the shift in oxygen 18 values represents the onset of YD climate change, coinciding with both platinum and ammonium peaks. Ammonium peaks marked with triangles are the 2 highest within the last 120,000 year record.
Man.
They occurred during an apparent ramp up in biomass burning activity beginning at the onset of anomalous platinum deposition.
So I have a question about this. I mean, this looks like there's a huge biomass burning associated with the sudden cooling.
Mm-hmm.
And then there's a even bigger biomass burning associated with a sudden warming.
Well,
so it's like
either way, if you have any kind of adaptive, if your biomass is now adapted to some extent, any climate change that severe in either direction is going to cause biomass die off. Now, I don't know if that's the explanation, but that's got to be part of it.
Right. So you could say that we just don't have a high enough resolution to see that the climate change took place first, then there was the die off, and then all of that caught on fire eventually because it was dead and dry. Is that kind of what you're getting at?
Yeah. That's what I'm getting at.
Can you determine, or would it be pure speculation, whether it was windier, or is that a natural result of there being less biomass, or can you predict
well, I
the
think
weather changes?
in the papers I've read, and maybe it's in this paper, that was one of the considerations, that it probably was windier. Now, could that be attributed to the destruction of biomass and creating a barren landscape? I don't know.
Drastic temperature changes, though, would cause in either direction would cause windstorms for sure.
Yeah, I would think so. Yeah, absolutely. Yes. And so here we have kind of this mythic motif of the wasteland, right? That has found its way into so many archetypal models, and still reverberating today, even throughout popular culture. The idea of the wasteland. Think about. I bet you we could think of some.
Book of
Parsifal.
Eli.
I mean, the Grail myth has the
Eli,
wasteland.
right. Yeah. What were you saying there, Russ?
I was just saying, like the Grail myth.
Well, of course, yeah.
The king being associated, the wounded king being associated with the wasteland, the Fisher King.
Yeah, exactly. And then think Road Warrior. I mean, we started thinking about there's a lot of these movies that
Walking Dead,
post-apocalyptic.
Yeah. Lord of the Rings, has very much the idea of Mordor is very much the archetypical wasteland.
The Dark Tower.
Yeah. So that's basically all those gray graphs showing the chlorine, the calcium, the magnesium, the sodium. That's crap that's blowing off of a barren. It's in loaded dust that's blowing off a barren continent.
We see in the sky around here in Texas sometimes when there's like big, massive dust storms in Africa. The dusts blow all the way over here, and then suddenly the whole sky is hazy and everything for days. It's crazy how.
Well, yeah, and that can show you how some of these very tiny microscopic impact proxies could be distributed about the globe.
Right, and you can imagine in the future, people taking ice cores will be able to see from that those dust storms happened.
Yeah,
Because
surely that's getting deposited on the glaciers.
Yeah, and also it'll be deposited in lakes. Might have a lot of dust that falls into a lake that can show up as a lamination in the lacustrine cores that you take from the bottom. But then also the idea that, if you've got a barren landscape and now it rains, you've got a lot more erosion moving crap into the creeks and streams. So the streams now become choked with all of this sediment that would normally be, we talked about this last week, I guess it was, when we were talking about the Channel Islands, right? And the evidence that you basically had a burn off of the walls, leaving them impoverished for a period of time when the forests, the juniper trees, the cypress trees, the pine trees got burned off, left a barren landscape. It was subjected to erosion. Now you had mass wasting events. So in the bottom of the canyon, you've got this buildup of these events, right? You've got at the bottom, you've got the signature of the biomass burning correlated with the impact proxies, and then you've got evidence of mass wasting and landslides on top of that, right? So right there, that's what we were talking about. So you'll have this accelerated erosion that will carry material into the creeks and the streams. Those streams will now, say wherever they might flow into a lake, right? That material now gets carried into the lake. It settles down and leaves very distinct signatures, stratigraphic signature in the bottom of the lake, where you can see that all of this material being flushed in is indicating intense storminess and or accelerated erosion. And we're going to be looking at some of those lake records, because many of those lake records show that there have been periods in the past where storminess increased substantially over anything we've experienced in modern times. And that's going to be very interesting. And maybe that's where it's going to get a little controversial, because of the fact that we're going to show that there's nothing that has occurred within the last century that's abnormal. But that's another.
Well, I just have to say a quick aside that Mass Wasting Event is another great band name from Randall Carlson.
Look, if I could start, maybe I could start, we start accumulating these and archiving them, and we could perhaps sell them. I mean, how much would somebody pay for?
We should have a place on the new website with a list of possible Randall Carlson band names.
Yeah. Now, I like that.
Buy the URL, and then you own it.
All right. Well, let's get back to some science.
Nanodiamonds.
Well, we're not going to talk about nanodiamonds yet, but we're coming up. I mean, that's like you were saying earlier, Russ. Nanodiamonds are a pretty definitive proxy, and one of the interesting ones. And we're going to definitely learn more about nanodiamonds, and we may get into that next week, if not next episode, certainly the one after. Okay. And then we'll kind of wrap up for now our examination of the fingerprints of catastrophe, and then begin shifting over to the footprints of catastrophe. And at that point, we're going to start looking. This is, I love this stuff that we're getting into, but, we're dealing with microscopic stuff here. And at some point in the near future, we're going to have a laboratory where we have all of these equipment, where we can use the scanning electron microscopes, and we can use the various equipment, and we can do our own original research. Boy, God, that would be just exciting to me. That would be like if there really was a Santa Claus, if there's really a Santa Claus out there, listen to me, man. That's what I want. Just in case. See, I never completely let go of the Santa Claus archetype. I always thought maybe somewhere back there, this guy really exists. And he might be out there somewhere, right? I can still remember when Christmas of 1957, when my dad's buddy dressed up like Santa Claus and came out to our house, and I thought he was the real deal. But then the problem was he was such a hit with me and my brothers that he came back the next year, and I was a year older, and I looked at him, and I got really suspicious. I recognized him. And the guy's nickname was Fish. So after he left, he came in, he pounded on the door. This is my dad would set up stuff like this. Pounded on the boom, 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 opens the door. Ho, ho, ho. Here comes Santa in with his bag of stuff, handed out the toys. Me and my brothers, my God, we were just like completely ecstatic over this whole thing. Well, the next year he comes and he does that. And after he leaves, I go to my dad and I go, Dad, how come Santa Claus looked like Fish? And he says, sit down. I got to tell you something. Says there's no Santa Claus. That was
there. Man.
And my first reaction was, yes, there is. I was not ready to give up Santa Claus. But however, on the bus after Christmas vacation was over, I was the guy out there in the bus telling all the rest of the little kids.
Oh, man.
Yeah. I said, look, extraordinary claims require extraordinary proofs. Okay. This is
the chimney math just doesn't work.
That's right. Starts busting on paper. Look,
the chimney math just doesn't work. And let's see, how many households is he going to have to visit in one night? So if he spent 45 minutes at our house. However, the point that I'm trying to make here in all seriousness, I've never completely 100% come to believe that there's not a real Santa Claus.
He could be out there. I agree.
He could be out there.
And he needs to bring us a full geophysics lab. I completely agree with that.
Here's the thing. When if and when we ever get into talking about symbolism and where some of these myths come from, because they all have extremely interesting origin stories. All of them. And all of them have their roots back in very deep and profound traditions from the archaic past. Pretty much every single thing, even no matter how superficial it appears sometimes, hell, the Easter Bunny, right? What's the origin of the Easter Bunny? Well, we have to go back to the Middle East thousands of years ago to find the origin of the Easter Bunny. It's not like somebody just, hey, made that up, let's make that up to get the kids excited, like, 50 years ago or 100 years ago. No, it goes back, way back. So anyways, geomythology, astromythology, all of this stuff contains very valuable information. And that's going to be one of the things that we do. We're going to peel open some of those myths, and we're going to extract some of those really weird details that are in some of those myths. And then with the backdrop of this information that we're looking at here, we might just be able to tease out extra, hidden layers of meaning in some of those myths that have been handed down from who knows when, long time ago. We just mentioned one of those, the Wasteland. You can go back and you Kyle, you mentioned, well, yeah, it played an intrinsic part of the Grail romances of the High Middle Ages. And there's a reason for that. Because you remember what was the whole purpose of the Grail quest, right? You mentioned, you said, well, the king was in decline, right? The king was declining. He was sick. He was infirm, right? But so was the land. The land was infirm. And what was the objective of finding the Grail? Well, the Grail was the antidote. The Grail was the cure. And it not only would cure the king, it would also cure the debilitated landscape. And once you begin to really go into that, into the details of it, you discover that there's a lot more there than meets the eye. And if it's not completely woo-woo wacko, completely a subjective interpretation, what we're left with is that just like somebody who built some pyramids in Egypt thousands of years ago knew way more about astronomy and geometry and engineering and social organization, et cetera, than they've been given credit for. We can also go back to the Middle Ages, and we'll find that there was a whole lot of people there that were part of a system that somehow had access to information that was out of the context of their time. And we see that. I mean, it's right there blatantly presented to our faces in the form of these Gothic cathedrals and everything that's displayed there. Because, you know, those Gothic cathedrals are instruments of alchemy. And they display the idea of the alchemical ideal right there on their facades. The first thing when you're looking at one of the high Gothic cathedrals, boom, what's it telling you? Hermetic knowledge, alchemy. Now, whether you believe in alchemy or not is not the point. The guys who built those cathedrals did believe in it. The guys who designed those cathedrals, they did. That's the point, right?
And there was a technology for the restoration of the wasteland.
And there was, yes, and that what Brad just said, I think, is the implication of the whole Grail mythos. See, we know now that events are in the history of this planet that basically lay waste to an entire region, landscape, perhaps even a continent, are very real. And that they've happened recently enough that it's in the memory of the living memory of modern human beings. So it's not any extravagant or outrageous conclusion to think that these kinds of things found their way into the stories, into the traditions, into the mythologies, into the legends, into the folklore. You see what I'm saying? Does that make sense? So that's our approach to this stuff, because when we're looking at these graphs of biomass burning proxies, we're seeing ammonium, we're seeing the nitrates, we're seeing the signature of the chromium, and going, why did suddenly there was all of this extra? I mean, chlorine. Why was there the sudden influx of chlorine? Why was there the sudden influx of these other substances? Well, then you begin to think it through, and you go, okay, well, here's where it came from. And it was not coming from this landmass when it was hosting vegetation. The landmass had to be clear to the vegetation. Now you've got the wasteland. And, if any of the Clovis people survived into the Younger Dryas, then they were contending with the wasteland. And the thing is with that final terminal glacial warming that preceded the Younger Dryas, the warming that basically persisted through the bottling and through the Allerod, it actually created a world that was becoming more livable, because the glaciers were melting, they were receding back, and so you had like whole new land areas that were opening up for colonization, right? And apparently the Clovis people, they were taking advantage of that. They showed up from wherever they showed up and left their toolkits and their artifacts all over the continent, and then boom, they were gone. Right there at that vertical dashed line, they're gone. So we got a confluence of some really on here, right? And I think the more we delve into it, the more interesting it gets, the more mysterious it gets. But to me, what's exciting is when you really begin to get enough data and enough of the details that you can begin to see the outlines of a picture taking shape. So let's go on and look at one more graph. I will move this up and we'll do a share screen. And we'll do that. Okay. So these are combustion aerosols from Greenland Ice Core Project. So A through D are coeval peaks here's your ammonium, right? Now the dashed line represents the platinum spike, which is being used as the datum, right? Coeval peaks in ammonium, acetate, oxalate, and formate, respectively dating to or near the Younger Dryas onset and representing the highest or near highest episode of biomass burning of the past 120,000 to 386,000 year record. Now, all of these are things that are combustion aerosols. They're formed by extreme heat and combustion of enormous amounts of biomass. So each one of these things, you'll notice spikes precisely at that platinum line that marks the climate change. So yeah, and then down here is the ratio of ammonium to formate, which is 2 strong indicators of biomass burning. The 2 highest ratio values in the record comprise the single highest peak at the Younger Dryas onset. So
yeah, so those 2 dots that are it says YD and it's got an arrow to those 2 dots are way up in the numbers of the graph. All the rest of those dots clustered down in the lower left corner are from all the other readings they've done in the past 386,000 year span.
Exactly.
That's amazing.
It is amazing. It is truly amazing. So they're talking about that there are 4 separate lines of evidence in the GISP core that demonstrate that a series of highly anomalous changes co-occurred within a relatively thin ice section spanning a mere 15 years between 12,836 and 12,821 calibrated years before present. You know, think calibrated, think also calendar is a little mnemonic. So this is the actual now, because radiocarbon years can vary quite a bit. So this demonstrates that the Platinum anomaly marking the Younger Dryas boundary impact event is synchronous with a peak in ammonium concentrations, an abrupt increase in dust concentrations, and then it says there, YD windiness, reflecting a shift in atmospheric circulation, and a drop in oxygen 18 values at the onset of the Younger Dryas cooling. This supports a strong interrelationship among all these processes. So then you combine that with the fact that you have the disappearance of the megafauna spiking right there. I would say that it suggests that there is a correlation, a major correlation.
So after they overkilled, they overdusted everything.
Yes, right. That's right. Right. And here we have nitrate concentrations in the ice sections, nitrate also being a proxy for biomass burning. You know, it's 15,000 years ago, and then right there, you have this spike in nitrates, which is nitrogen trioxide. You have this spike there, and then throughout the next years of right there, as you see the beginning of the Holocene. And it's reflecting a very different environment after notice the difference here in the Holocene compared with the late Pleistocene. And then your Younger Dryas is the transition between the two. And what you have then at the onset is this nitrate spike. So yeah, that's from Antarctica. So it shows up in the Antarctic ice core abundances of nitrates, a biomass burning proxy, age correlated with the Greenland Ice Sheet Project 2, Platinum Peak, and the Younger Dryas onset, which is the vertical dashed line. So here is so there's the onset is marked by the Younger Dryas, by the Platinum deposition in the ice. So I'm going to stop share then. Okay, I'm going to do another graph here while we're at it, which is an interesting one in its own right. And we will do, here it is. If we look at this, here is that 21-year episode, right? We've got Greenland Ice Sheet Project 2, Platinum, and volcanic sulfate, volcanic SO4. Platinum deposition is represented by the black curve. And notice you're coming 13,000 here, 12,700 years. So again, it's a 300-year span. But then also notice that you have sulfates represented by the dashed curve, and the sulfates are the result of volcanic eruptions. The vertical gray bar, again, represents the JISP2 Platinum anomaly dating from 12,836 to 12,815, calibrated years before present, with a high peak centered right at 12,822, with the data, see the dotted line up there? None of the 4 highest volcanic sulfate peaks corresponds to the Platinum anomaly. But it's interesting that you see that the Younger Dryas is bracketed by some pretty significant volcanic eruptions. This over here is the Locker Sea.
That's the onset, right? The onset of the Younger Dryas is bracketed by.
Here's the onset. This is the onset of the, yes. This gray bar is the, you could think of as that's that 20-year span at the beginning of the Younger Dryas where platinum is being deposited into the Greenland ice. So you had a couple of substantial volcanic eruptions leading up to it, and you had several that came right after it. So I would venture to say that if we go back to 14,600 years ago, when you had meltwater pulse 1A, that right in there, you had major melting and major shifting of glacial mass from continent into ocean, and that this lateral transfer of mass would have been responsible for accelerating or enhancing volcanic activity. And I think we might be seeing that here, is that because there were so many changes going on. Again, we were talking about what I was talking about earlier, exogenic versus endogenic, from without versus within. So we have yet to explain meltwater pulse 1A at 14,600 years. To my knowledge, we haven't found impact proxies there, but I'm asking, well, has anybody actually looked? But part of the problem would be is that the events of the onset of the Younger Dryas were so severe and so chaotic that it may have
obscured it.
Skewed, really. Yeah, it may have. That's my fear of it. That. So
surely there's somewhere where it's preserved. It can be.
One would think.
Yeah.
So the paper goes on to say that well-dated, high-resolution ice core sequences are crucially important for providing records of biomass burning during the late Quaternary. Peaks in ammonium are the most, or NH4, are the most widely employed proxy for biomass burning in ice cores, strongly supported in some sequences by other combustion aerosols. And that is, of course, like we just saw, oxalate, formate, and acetate are all combustion aerosols, byproducts of intense biomass burning events. Several ice core sequences have revealed clear evidence that the onset of the Younger Dryas is intimately associated with one of the highest and most pervasive late Quaternary peaks in each of the ammonium, nitrate, formate, oxalate, and acetate. These peaks are effectively coeval, meaning at the same time with abrupt cooling and other climatic effects, marking the onset of the Younger Dryas episode. And then also, they point out that carbon dioxide values mostly increase before the Younger Dryas onset, after which they exhibit a abrupt rise followed by a gradual long-term increase. Although degassing of the ocean to the atmosphere during deglaciation contributed to this generally rising pattern, the abrupt rise at the Younger Dryas onset is consistent with a brief episode of major continental biomass burning. And that is because carbon dioxide is released through biomass burning. And then we will go back to our share screen again and looking at this particular, so this is the Younger Dryas boundary biomass burning proxies plotted against impact-related proxies from 10 selected terrestrial sites. So here, Arlington Canyon, we were talking about that, right? Blackville, South Carolina, Blackwater Draw, New Mexico. That's the archaeological, paleontological site that's just very near Clovis, New Mexico, right? From which the Clovis culture gets its name, right? Bull Creek, Oklahoma, Halls Cave, Texas. That's the one you guys were looking at as far as with Stafford, right? Yeah.
Yes, sir.
Yeah. Okay. Lake Hutio in Mexico, Melrose, Pennsylvania, which we've been talking about. Remember, microspherules? And those microspherules were traced to that small little region
Yes.
at which Lake St. Jean is almost dead center in that region,
Right.
that provided the unique and specific geochemical signature of the Melrose microspherules. Okay, Murray Springs, Arizona, Newtonville, New Jersey, Sheridan Cave, Ohio, right? So we've got 10 different sites. And if you look at them, you'll see that the black solid lines represent either platinum or magnetic spherules. So basically, the dark lines represent, as it said, either the platinum or the magnetic spherules, because both of those are impact proxies, right? The dotted gray lines represent aciniform carbon, which is a type of soot that is formed in extremely hot combustion events, sometimes actually out of biomass. The intense burning of biomass itself can produce aciniform soot. Black carbon, which is just another form of soot that is also produced. The aciniform soot is unique and it has this grape-like cluster, right? So it's a little different than the black carbon soot, but they're both evidence of major biomass combustion events. Or charcoal. So you've got aciniform soot, black carbon soot, and charcoal. All of those represented by the dashed lines. The dark lines, solid lines, then represents either the microspherules or the platinum. And in each case, you'll see that the biomass burning coincides with the deposition of the impact proxies at 10 different sites. That's what this is telling us right here. Each one of these cases, you'll see that there's a very close correlation. Here, the platinum, huge spike in platinum right here at Melrose, Pennsylvania. And then here is your biomass burning spike right there in terms of the dashed line. Here again, look at in Mexico. Here's your biomass burning, and here's your platinum deposition right here. Let's see, it's a platinum. No, this is magnetic spherules. In this case, it's magnetic spherules. So notice that the biomass burning proxies are a little bit earlier, a little bit deeper, and then the microspherules are on top. So apparently you would have had this biomass burning, and the soot and stuff comes down first and settles, and then these microspherules begin to filter out of the atmosphere. And so they are essentially above the soot layer. And here at Arlington Canyon, you can't really even tell the difference. The biomass spike is precisely superimposed upon, in this case, it's the platinum. And here it's aciniform soot. In Blackville, South Carolina, platinum, aciniform soot. At Blackwater Draw, it's platinum with charcoal. And the dashed line is charcoal. So again, notice the charcoal, the coincidence between the charcoal and the platinum deposition. At Bull Creek, Oklahoma, aciniform soot and platinum. So you can go through these and you see the same thing. So here, Sheridan Cave, Ohio. Here's look at the platinum spike, and then you have a black carbon soot is the dashed line. So you got to come up with a theory that can explain this juxtaposition of known impact microspherules, or known impact proxies, and biomass burning.
Yeah, so
again, Randall, oh, sorry, Kyle.
Go ahead.
You're looking at these at around 12,800 to 12,900 years ago.
Yeah.
Which is, we've come up against this multiple times. The younger Dryas was a 1,300-year period, but a lot of these evidences are showing from the beginning of that period.
Yes.
So that was the Bowling Alarod younger Dryas, right? And then there's 1,300 years, and then it's the younger Dryas pre-boreal.
Yes.
Right. So we've got the younger Dryas. We know is that 1,300-year period, but we've got a name for the start of it where we're looking at a lot of these evidences, and then we've got another name for it coming out of the younger Dryas to then what comes into becoming the Holocene. So
yes.
We're running short on time here, but I want to clarify that because we've come up against that multiple times, because a lot of these evidences are at the beginning of the younger Dryas, or the Again, what I just said there was the bowling Alarad younger Dryas. Yeah. So yeah, unfortunately we're short on time here, but yeah, I wanted to clarify that.
Well, let's just conclude with my last extract from this particular paper. So here, towards the conclusion, they're saying that the sudden rise in carbon dioxide at the younger Dryas onset, recorded in Antarctic ice, is 2.44 parts per million, because each part per million is equivalent to 7.805 gigatons of carbon dioxide in the global atmosphere. The recorded rise corresponds to the release of just under 20 gigatons of carbon dioxide. Vegetation fires produce approximately 1.95 to 2.23 times 10 to the fourth kilograms per hectare of carbon dioxide, if anybody wants to, check out these numbers. But here's the point. If the observed jump in carbon dioxide were due to vegetation fires, it would be equivalent to the surface burning of roughly 0.94 times 10 to the 9th hectares, or roughly 1 times 10 to the 7th, or 10 million square kilometers. 10 million square kilometers is about 3 million, is just under 4 million square miles. So to get an idea of what we're talking about, is we're talking about an area that's roughly the entire North American continent that was not glaciated. So that's about what it would be. You would have to, that's the minimum. It would be if you have the picture of North America, including Alaska, including parts of Beringia, and all of the southern unglaciated down into Mexico, you're looking at just about under 4 million square miles. So you're looking at a firestorm that would have had to consume that much biomass, and probably did it, within a matter of initially a matter of days or weeks, because once those fires
scale.
What?
Continental scale.
Yes, you're talking about continental scale firestorms. So you have to think of if an equivalent firestorm today, you could basically, if you took all of the United States and Mexico and it was completely forested, and then you burned the whole thing up in one massive firestorm. That's about what we're talking about here. So yeah, it's very close in area to the whole area of Canada. That's very, very close to the whole area, which is just under 4 million square miles.
That may explain where all the Clovis went. If the whole continent's on fire, there's not going to be anything left of them.
Yep.
Right.
Again,
Wasteland.
Yeah, the wasteland. And then if they do survive, there's nothing to eat.
Brad's got his hat on.
So means we got 5 minutes left. Okay, so next episode. What we're gonna do?
Is that what that means now?
Way to ease into that, Randall.
Well, we're just letting people know this is the way it's going down. Brad is basically laying down the law here. And as we were talking about earlier, myself, Mike, you weren't there, but myself, Russ, and Kyle, we have all been exposed to the evil Brad. And I don't think you ever have. So, but we know from experience, we do not want to release the evil Brad under any circumstances.
Because I know enough to not go drinking with him.
All right. So
then we're going to go on to the second paper, because what we've just been looking at is ice cores. So we're going to go on to the second paper next episode, which is where we're going to look at lakes, the oceans, and the terrestrial sediments, and see what we can find when we look there, and see how that correlates with the ice cores and the glacier cores. This is going to be some pretty impressive stuff. If we've got 1 minute left, I'll introduce it. To better understand potential younger Dryas boundary biomass caused by previously studied cosmic impact events, one of those, the Tunguska airburst in 1908, over Siberia created impact-related magnetic spherules, melt glass, nanodiamonds, and iridium. Got those 4 things? All byproducts of the Tunguska event of 1908, which we're going to delve into in great detail coming up, okay? Magnetic spherules, melt glass, nanodiamonds, iridium. This air burst produced a high-pressure blast wave, energetic enough to topple 80 million trees across approximately 2,000 square kilometers, which is over 800 square miles. The thermal pulse scorched trees near the epicenter before transient high temperatures rapidly subsided from more than 10,000 degrees centigrade at the center of the fireball. Numerous sampling sites at Tunguska indicate that temperatures and the severity of biomass burning decreased outward with distance from ground zero, initially igniting 200 square kilometers of forest and subsequently spreading to consume 500 square kilometers of forest. But when you're talking about more than 10,000 degrees centigrade, you're talking about the temperature of the photosphere of the sun. You're talking about, temporarily you have temperatures released there that like the sun. So, somebody in one of the comments, a couple of months ago said, well, when we were mentioning impact possibly triggers for glacial ice melting, somebody commented, well, there wouldn't be enough heat. And I obviously would beg to differ with that contention that there would not be enough heat, particularly in a multi-impact event. And I think more and more as we proceed through this massive evidence, we're going to come upon a scenario that is a multi-impact event and not a single.
Awesome.
Yeah, man.
Wow. Great show. Great content. Thank you.
Outstanding.
Yep. Yeah. I think that was part of that 21-year band, right? Was basically showing us that there was this deposition of platinum that was happening over a 21-year period. That would imply a bombardment as opposed to a single event in some cases.
Maybe so. That there was an injection. Yeah, somehow we have to explain this 20-year, 2-decade injection of platinum into the atmosphere. Was it all injected at once and then took that long to settle out? Or were there repeated injections over so that's the question. I don't know the answer to it yet, but we'll see. Maybe this subsequent paper has some insight into that. Yep.
And we'll get into that next episode. So we thank everybody for sticking around with us. And you can get a hold of us, Kosmographia1618@gmail.com. We are getting new email addresses. Is that right, Brad? We're all going to soon have new ones.
They're set up. We'll probably announce them next episode, along with the release date for the new website, randallcarlson.com.
All right.
And notice behind Brad, this is an example of some of the kinds of artwork and illustrations that are going to be featured on the new website. Yeah.
Beautiful artwork there.
To help people really begin to visualize the things that we are talking about here. So.
All right. So new website coming up. Thanks, everybody. Really appreciate it.
Thanks
Check
so much.
the show notes for all the details, papers, and other links that Brad puts in there. Good night.
And we will say there we've talked about it multiple times, but not necessarily this episode. There is a email address already active if you know about the trips we're taking and planning.
That's right.
tours@randallcarlson.com is the email. You can check in with us and get on the list. If you've been paying attention to which trips we're talking about, make note of that, and you'll be first in line. Tours@randallcarlson.com, and that will be in the show notes and the descriptions.
All right. Good night, guys.
Good night.
Thanks for the show.
Good night.